just heard an excellent colloquium by Rahul Kannan, where is he? Over there. And he spoke about the dark ages and the first generation of galaxies, and he will tell us some more in a few minutes. After him, we'll hear Dillon Brout from BU, not very far from here. Where is Dillon?
Yeah.
Oh, okay. Right there. And he will tell us about the local distance network, a community consensus report on the measurement of the Hubble constant at 1% precision, meaning that we should worry about systematics. And then we'll hear from Majo Colmenares from the University of Michigan, over there, who will tell us about exploring the organic reservoir of the inner disk with JWST. And finally, we'll hear from Theo from Harvard, who will tell us about the intermediate velocity and high altitude clouds in the solar neighborhood. Rahul, please.
Yeah, thank you, and thank you for the opportunity to give this talk. So, for the short talk, I'll talk about how to a model for POP3 star formation in cosmological simulations, and this work is in collaboration with my master's student Bipradeep Saha. When I mean collaboration, he did all the work. Okay, so let's talk about POP3 stars. So these are the first generation stars in the universe, and they have this composition set by Big Bang nucleosynthesis. So basically, hydrogen and helium. And since you do not have any metals in this very early universe, you have very inefficient cooling, and which can lead to, because where you have very inefficient cooling, your Jeans masses will be higher, which means you are expected to get a top heavy IMF for these population 3 stars. And this work has been shown a lot more than 20-25 years ago. But then once these POP3 stars form, they enrich their surrounding with their metals and allows the gas to cool more efficiently, which can lead to disk fragmentation, and which in turn is theorized to produce like saltpeter-like or Chabrier-like IMFs in the later stages of the universe. And there have been a vast array of models which try to follow the formation and growth of these POP3 stars and first galaxies in great detail. And there also have been recent semi-analytic and simulation efforts which have tried to place the formation of these POP3 stars in a cosmological context. And here I show an example from a review paper showing a lot of different semi-analytic and simulation models which show the star formation rate density in the universe of just POP3 star formation. Okay. And with JWST observations, potentially observing galaxies during this cosmic dawn with current observations at redshift 25 or 30 or so, it has become extremely important to include POP3 models in modern cosmological simulations. Okay, that's just an introduction. So in this work, I'll try to give you one model which we have tried to implement into this Thiessen-Zoom framework that I call it. So before implementing this POP3s, Thiessen-Zoom kind of followed a non-equilibrium thermochemistry of molecular hydrogen. It had some formation on, so most of the H2 was forming on dust grains. The gas phase reactions were not well modeled. I'll come to that. And then we had radiative transfer coupled to it, so you can know how much amount of Lyman-Werner radiation is present, for example, which is important for H2 formation and destruction. And it also had a simple model for feedback from stars and supernovae, but mainly POP2 stars. So all of this was in the context of POP2, POP1, and not really POP3. Okay, so the IMF was Chabrier. Energy feedback and metal enrichment routines were from POP2. None of this was POP3. So in order to include POP3, the first thing we needed to do was to extend the thermochemical network. So the current thermochemical network as it exists in these in our simulations follows neutral hydrogen, ionized hydrogen, neutral helium, singly and doubly ionized helium, and a model for H2, molecular hydrogen. However, it is an extremely simplistic model, It kind of works well in high metallicity environments because most of the H2 forms on dust grains. But in low metallicity environment, the point is these H2 formation is mediated by intermediate ions like H2 plus and H minus using these equations here, chemical reactions here. But we did not really model these reactions as such. We just used an effective reaction rate to model these reactions, which is not necessarily valid in all conditions. So what we did, the first thing we did was to go from this chemical network to a chemical network which also follows the formation and destruction of H2 plus and H minus, so that you can also follow these kind of gas phase reactions, which are really important for H2 formation in these very low metallicity, low dust environments. Okay. So this is the extended thermochemical network which will be useful for these low metallicity environments. In addition to that, these additional ionic species like H2 plus also allows you to cool to lower temperatures. So the collisions between H2 and electrons and H2 plus and electrons and H2 plus and neutral hydrogen can also have additional cooling terms. So previously we only considered collisions between H2H1 and H2H2, but if you can follow these additional ionic species, you can also follow how much these ionic species cool. Okay, so we and this is what is shown here. So that's the effective cooling rate as a function of temperature of the gas. So previously we followed the bluish grayish line and the pink line. So those were the cooling rates previously implemented. Now we also have these additional cooling rates from these additional species. Okay, so then we test this extended thermochemical model in a Stromgen sphere test, where we put a star with a surface temperature of 4.3 times 10 to the 3 Kelvin in the center of a box of pure molecular hydrogen, and we do radiative transfer calculations to see how it behaves. So you can see here that after some amount of time, you set up a Stromgen sphere. So in the center of the Stromgen sphere, it's fully ionized. You have a layer of neutral hydrogen, and then beyond that, you have just H2. So it seems to work. And this is the quantitative plot showing the evolution of the Stromgen sphere as a function of age. The solid lines are this new extended thermochemical model, and the dashed lines are without the previous model, which was more simplistic. You can see there are differences in the abundances of H2, for example. More importantly, what you can also see is these additional cooling channels, which I talked about, will cool the gas will only heat the gas to lower temperatures within the Stromgen sphere. So that is, so if you have these additional channels, that is the red line here, then you only heat the gas up to like 9 times 10 to the 4 instead of 14 times 10 to the 3. Oh, 10 to the 3, not 10 to the 4. Okay, so that seems to work. Next is you need to figure out the radiation output from POP3 stars, because again, the previous models that we had, we only talked about radiation from POP2. POP3s can have, of course, much larger radiation and much more harder radiation, because if you have a top heavy IMF, the surface temperatures of these stars are much higher, and so you'll have radiation in the much harder ionizing bands. So what we did is we initialized about 100 metal-free stars from 0.1 to 500 solar masses with Webian proportions, and evolved these stars using the MESA code. And then from the MESA code, we took in the effective temperature log G and the composition, and we fed it to this radiative transfer code called +T, which does all the radiative transfer calculations for you and gives you an output of the spectra. Okay, and so the output we get is this one here. So the blue line is the radiation output of POP3 stars, assuming a log flat IMF, and the green line is the BCO3 IMF, which is Bruzol and Charlot 2003 IMF of just POP2 or POP1 stars, what you already say. You can immediately see that we have higher radiation, and we also have much harder radiation in these POP3 stars. The other thing we did was to also model feedback and metal enrichment from these POP3 stars. So in all models, like POP2 models, we assume a canonical supernova feedback energy of about 1 to 1.2 times 10 to the 51 ergs. But these very high mass stars, which are about 140 to 260 solar masses or so, they can go pair instability supernovae, and they can inject a lot more energy into the ISM than just pure normal supernovae. And so we kind of include that as well. So from 0 to 100, we assume a normal 10 to the 51 ergs injected. From 100 to 140, I think there are models tell us that these won't explode, they just form black holes, so we don't inject any energy. And from 140 to 260, we use this relation to inject the energy from pair instability supernovae. Okay, and so we performed a set of simulations. Again, I will caution that this is extremely preliminary. We just started analyzing them. We don't know if everything works properly, but these are the set of results that we got. So we ran 4 simulations. One was the usual fiducial model, one with an extended thermochemical network, the other with a POP3 log-flat IMF, then a POP3 with a salpeter IMF, and the fourth one with a POP3 with a log-flat IMF, but now the maximum mass of stars is about 250 solar masses. Okay, and so this is how the gas mass in the simulation behaves. So the bottom panel is redshift, and the x-axis is the mass of the gas. So you can see that the mass of neutral hydrogen. Let's concentrate neutral hydrogen, which is just the solid line here. The mass of neutral hydrogen keeps increasing as a function of redshift in these models without POP3. But as soon as you include these POP3 models with their very high radiation input and supernova input, the amount of neutral gas seems to decrease drastically. Okay. The same with stellar enrichment. These POP3 models seem to enrich the surrounding ISM and IgM to a large extent. You see that carbon, nitrogen, so you have to look at the pink and the gray lines here. So the carbon, nitrogen, oxygen are much more enhanced at very high redshift compared to models which are blue and orange, the green and orange, which only enrich the ISM, seem to be at a later time. Okay, so conclusions: we have extended the thermochemical network to better simulate gas phase reactions that give rise to molecular hydrogen, developed a new stellar spectral library for POP3 stars, and we have developed realistic feedback and enrichment model for POP3 stars. And to do, we just have to investigate what this is telling us, because it's still very, very preliminary. So thank you.
So Rahul, these population 3 stars are suicidal because they die within a few million years.
Yes.
And they enrich the medium around them with heavy elements that prevent future star formation being POP3. So in a way, they kill prospects for making more POP3. So it's one generation, that's it, and they disappear after a few million years. So that means that it's like an explosive event, and then after that you do the standard calculations. And is that the way you incorporate it? Yeah.
Yes, so the way we incorporate it is that we put a metallicity limit on the stars. If it is less than a certain metallicity, we say it's POP3, otherwise it's POP2. And that's basically what happens. I don't have a plot here. Maybe I have a plot here. No, I don't have a plot here. But you can look at the fraction of POP3 stars as a function of time. And it's like a step function. You have almost 100%, and then it drops off quite quickly, and then it's mostly POP2.
Right. Umesh?
Yeah, on bullet 4, the to-do.
Yes.
You showed us the spectra.
Yes.
And the continuum spectrum looks very different. One is much harder, right? The
Right,
POP3
yes.
gas. That's going to be right in JWST band.
Yes.
So,
Yeah, we have to do.
people noted that they look harder or anything? Should be
No, they're looking for like these helium-2 lines, which should
forget
be.
the lines. I'm just looking at
No, it's
broadband
absorbed.
color.
It's absorbed. The UV is
Broadband.
absorbed by the intergalactic medium, so
Is it?
you can't see that UV part because it's
Yeah.
absorbed by the intergalactic medium.
Oh, I thought these guys were kind of ionizing everything.
Ah.
Much less gas.
So these POP3 stars, if they exist, they should exist at very high redshift,
Yeah.
which means that if you have Lyman continuum, Bow-Lyman continuum, their mean free path will be low because our universe is not reionized yet.
Not yet. Okay, that's obvious point. Yeah.
Yeah.
Thanks, Avi.
Devesh?
Yeah, thanks for the great talk. Just first question about modeling of these stars. Do you assume them to be rotating or not? Are these?
In MESA, no, we don't assume any rotation here. This is very simplistic. Sorry?
Because they should be rotating quite fast actually, and if they're rotating, then you know they should be much more compact and much more hotter, so the position in the HR diagram would change.
Okay. So you think they will have much harder spectra and stuff like this?
Yes, yeah.
Okay.
I think,
Yeah, I'm not a stellar spectra person, so we did the simplest thing we could do, but yeah, maybe we should consider that as well. Yeah.
One more question over there.
So the POP3 must highly ionize the surrounding rather than POP2. I wonder whether you could use the ionization parameter U as now the diagnostics to differentiate between POP3 and POP2.
Yeah. The lines that you see will be very different, I think. You won't see much. You have a harder spectra, so you will see lines corresponding to that compared to a POP2.
Okay, let's thank Rahul again. I should say while we are changing computers over there, there are two announcements. One, I exchanged emails with Roseanne Di Stefano that there is a new mentoring program, Mentoring Constellation, and there is a new cycle that allows one-to-one mentoring at the CFA. You need to register. There is a form that will go to all the CFA staff about it. And you contact Roseanne if you have any questions. And that allows you to mentor younger people, like students, postdocs, and any other research fellows. And then in 2 weeks, we have a special event that combines art and science. It's an unveiling of 51 watercolors and 2 bronze sculptures. And that will take place after the ITC lunch on Thursday, November 13, between 2 and 3 p.m. At the Walbach Library in the lower level. And you're most welcome to join. There will be the artist that created this art, Greg Wyatt, who is quite famous. And then music by David Debet, who is the local composer in residence, with soprano Barbara Hill. So there will be some music and discussions about art and science. You are most welcome to join us.
Okay, that sounds very interesting.
Yeah, you are also welcome. Yeah, you're not far.
Thank you for having me. It's nice to be back. I'm now across the river. And thank you for the invitation to give this talk, because it was a really big motivation for us to get the paper out, which came out just a couple of days ago. And this is our first talk in public about it, so it's exciting for us to be speaking about the distance network. So not to be confused with the distance ladder, a decorrelated consensus framework towards precision H0, hopefully at the 1% level. This is really coming out of a workshop that we had, and I'll describe that on my slides. But as a reminder, you all know and love the Hubble constant tension or crisis. Here I'm showing 2 of the main data sets involved. Pantheon plus SHOES, so this is supernovae by Pantheon plus, calibrated by the SHOES distance ladder. And when you compare that to Planck or CMB, under the assumption of a cosmological model, lambda CDM, there's a disagreement that is becoming quite significant. Noting here, this is a direct, this is a direct measurement, and this is a measurement assuming a model for cosmology. Okay, so the distance ladder method by SHOES is one such example of how you could build a ladder where you calibrate from geometry to some intermediary distance indicator to some secondary distance indicator out into the Hubble flow where you can measure the Hubble constant. But there are many ways you can do this, and many groups have done this in different ways, and you can have different anchors in the bottom rung, you can have different middle rung alternatives, and you can have different third rung alternatives. And you've seen plots like this. The top panel are the model-dependent measurements, often from the very early universe. This talk is focused on the bottom panel here, the direct measurements, where there isn't a model assumption, and the community has gone wild over different ways to analyze different data sets, replacing different rungs of the distance ladder, and so on. But well, so this has actually been very instrumental in showing how systematics could impact measurement of the Hubble constant, but it's important to note this can be deceiving if you're just looking at H naught. No, it's not even labeled. H naught is this plot. They all have covariance, okay? These are just swapping out one of the rungs in many cases, and you still have other rungs that are consistent amongst these probes. It's more difficult to isolate individual rungs, which is really what the goal of what we did was. To what extent do these all actually agree? Or to what extent are they correlated? And if they are correlated but agree, can we combine them? And if we want to combine them, how do we combine them very carefully? So we convened the workshop at ITC in Bern, thanks to Director Antonella Nota for organizing it and for chocolate. And the goals were to convene the leading groups. All of the groups that you saw on the last slide, we tried to get to join us. And then together we would scrutinize and build some quality control measures and come to agreements through consensus. We then built out methods for combining data sets, evaluating systematics between data sets and covariance between data sets into a unified framework. This framework is now publicly available, easily pip installable. Anyone who has any curiosity over how to tweak anything in the now distance network, you can start playing around with that. And so that's one of the main goals of what we did, but really we developed a very clear formalism. It's essentially a system of equations that allows you to connect the relationships between all of the different rungs of the distance ladder and all the different probes in the different rungs of the distance ladder. It avoids double counting, it accounts for covariance, it allows us to check directly for consistency or inconsistency between probes without going to H naught, but looking at individual pieces of the network. Really, just going to H naught can be misleading. And so we're trying to avoid doing that. It's a modern tool set, and we're going to keep it alive, meaning that we hope that when you build data sets, you add them to this network, or at least use the network to compare to what you've done. And it makes it easier, because now if you want to make a measurement of the Hubble constant, you don't have to know everything about megamasers just to measure the Hubble constant. You can just plug into our network and see what Hubble constant comes out and see what, if anything, changes. Oh, and the last thing is you can pick a path. You don't have to take everything in the network. You can say, oh, give me the shoes path. And you just type shoes in your ini file, and it picks the blue lines through the network, or your CCHP, or whatever systematic you may be interested in. You can pick different paths through the network and compare them. For the sake of time, I won't be describing all of these, but you can use the slides to refer back. But we have in the first rung, the geometric rung, we have the anchors, megamasers, which are thanks to Mark Reed and Dom Pesci here, detached eclipsing binaries, and Gaia trigonometric parallax in the Milky Way. In the second rung, or really the primary distance indicators, we have, of course, tip of the red giant branch, we have JAGB, we have MIRAS, thanks to Caroline, and Cepheid's. And then in the third rung, out into the Hubble flow, we have surface brightness fluctuations, fundamental plane, type 1a supernovae, Tully-Fisher, and type 2 supernovae, which are calibrated and standardized very similarly to type 1a supernovae, but just not quite as accurate, but their own alternative. And we're always hoping to find viable alternatives to the supernovae, because the supernovae are really the strongest thing we have at high redshift. Okay, and then we do have two alternative paths that aren't a ladder in a sense. We can take the masers all the way to cosmology without doing a ladder. It becomes dominated by peculiar velocities, and we also have a astrophysically model-dependent type 2 supernova expanding photosphere method, but that's a bit more of an early work that needs a little bit more maturing. And that brings me to how we came to a consensus on what methods to consider in our baseline analysis. So this would be in the scenario where if everything agrees, which we haven't looked at yet, so far we're evaluating individual probes separately based on their methodologies, and we're voting on, as a group, which ones we believe should be in our main analysis. We haven't looked at agreement yet. And you see here these as primary distance indicators. We were almost completely unanimous for which ones should be included in the baseline. We also have ones that are included in the variance. Nothing was actually excluded, but we have two primary distance indicators that we decided to just look at in terms of systematics. And then secondary indicators, we have a couple that are used in the baseline and a couple that are used as variance in the analysis, which I'll show you. But then we can go and look at agreement. So now we've made a decision on what we're going to use. Now let's go plug it into the network and see what comes out. And these are distance modulus residuals for each galaxy as a primary distance indicator. So TRGB, Cepheids, and so on. You can see the individual galaxies, and you can also see these horizontal error bars are the systematic uncertainties, number one, reported by the individual groups in the measurement of, for example, Cepheids, and the systematic uncertainty, we'll call it, from the fact that you have to calibrate the Cepheids to some anchor, and that may not be the same calibration uncertainty that you get from, if you're using HST versus JWST. That will change depending on what instruments you use, what probes you're using. So really the take home here is that the systematic error bars reported for each of the probes are all, when you look at residuals, encompass the total scatter. It's all in agreement. We don't find any probe, after accounting for systematics and anchor uncertainties, disagree. So no disagreement. You can also do this when you go to the Hubble flow with the 3 Hubble flow baseline probes, and you can see here why the supernovae are so dominant. We have surface brightness fluctuations and megamasers, but these are at much lower redshift, and they're dominated by peculiar velocity modeling systematic uncertainties. But again, everything does agree within the systematic uncertainties reported in the analysis. And that brings us to our baseline result. You can combine everything now. It looks good. It's agreement, and we get 73.5 plus or minus 0.8. That's a 1% measurement. The reduced chi-squared is about 1. And we find good internal agreement, so that was exciting to see. And then we go into the variance. So we're going to dive into this if there's time individually. I'm going to zoom in, but the main thing I want to show you is that the variants are motivated by the community, motivated by our own discussions at the workshop, and specifically they're motivated by looking at something where you can actually come up with a hypothesis for why you want to look at a variant. Or if you want to examine like a specific instrument like HST or James Webb. We did not explore variance, and this was a consensus choice. We did not explore variance where we just start throwing out a bunch of data sets without any specific hypothesis just so we could try to get a weird H0 relative to our baseline. That was not what we're doing. Everything is motivated. Okay, so we have the add one in variance. The first section, here's our baseline result. The add one ins are the ones that we consider to be not first rank. These are the variants. You can see here there's minimal variation as you add in some of these other probes. Then there's the leave one out variance. If you don't trust any one probe, you don't trust Cepheids, you don't trust TRGB, you can see how things move around. Important thing in this section to note, it's worth going over time, is that the dotted line is really what you want to compare to. The dotted line is if I throw out Cepheids, that means I'm going to lose some of my calibrator galaxies. So let me compare to an analysis with Cepheids, but throwing out those same calibrator galaxies. That's eliminating a statistical variation simply by removing the Cepheids. So it's the delta between this solid line and the dashed line is what you want to compare to. For if you care about Cepheid systematics specifically. And there's similar scenarios here with the other dotted lines. And then we have other exclusions of instruments, no HST, no James Webb, and many other ideas for systematics. And remember, Planck is over here. Okay? And so at the end, we have 7.1 sigma across many variants that, generally speaking, are representative of our systematic error bars. And we're 7.1 sigma from Planck plus SPT plus ACT. It's also worth noting strong lensing, which is not considered in this paper, is coming in high. And so my final thoughts are the distance ladder and specifically the network remains extremely robust as far as we can tell. We don't see any explicit disagreement between any of the probes in the network. We argue that new data sets should plug in, or at least compare to what we're doing, and make things public, and make their analysis public, and make their data public. We've seen great consistency, good chi-squared, robust to variance, including leaving out any individual probe that you may or may not like, and then finally, we're at a crisis, I think. So, yeah.
So Dillon, 50 years ago, Steven Weinberg wrote a book on cosmology.
Yeah.
I remember studying cosmology from that. And he said, well, there are two groups that completely disagree. They hate each other.
Yeah.
One claims 50, the other 100. I
Yeah.
will take the average. He was not wrong by much.
Yeah.
My question to you is, so this higher value of H naught relative to the CMB would make the universe younger.
Yeah.
The age of the universe would
Yeah.
be smaller.
Mhm.
What does it bring you to? Like 13 billion?
I think it's about a delta of a billion, yeah.
A billion years, it's
Yeah.
a lot.
Yeah,
so
right.
now my question, so now there are stars that are older than that.
Yes, yeah,
So
yeah.
what do you do about that?
I was going to ask you that.
I mean, some people in this room might be older than that. So it's an issue.
Yes, it's an excellent new way to look at the problem. I love it.
Okay. Well, that's a challenge to people that use stellar evolution models to get the stars to be younger than 13 billion years.
Yeah.
Yeah. Okay. Ramesh.
So I had heard maybe a year ago or so, maybe Wendy Friedman was still going around saying that actually it's come down to 70 or whatever. Well, I didn't see that anywhere in your plots.
Yeah.
That has gone away. Was there?
So in our plots, we have CCHP specifically. So here, so this yellow path is CCHP. That's the path that they took for the analysis. I'll keep it relatively brief. There's been a lot of literature on the explanation for that 70 value. It comes down to really two things, actually, that we address yet again in this paper. So the first thing, why is F25 low? Okay, thank you for asking this question. It comes down to calibrator sample statistics, which we can very accurately account for now in this network. And number two, the SN model, supernova model that you're using. So let's focus over here. This is F25 calibrator sample. So Wendy's group had 24 calibrators with James Webb. And that means you have 24 type 1a supernovae in those calibrators. That is a statistical fluctuation. And you can compare that statistical fluctuation. For now, let's just pick the average of these points and compare it to the full calibrator sample, which is everything we have in the literature. And it is down by about, I don't know, 1 kilometer per second. So that explains about 1 kilometer per second difference is simply a statistical fluctuation of her smaller sample size. The other thing is that what we found, and fortunately we had some of Wendy's collaborators at this workshop, is that we were not, in the process of putting these data sets in, we also wanted to make sure we could reproduce them. And we weren't able to reproduce Wendy's analysis because we were using the supernova model in blue, which is the latest one reported by her collaboration, the CSV collaboration. And what we noticed is that in the F25 paper, they're using this supernova model. It's an outdated one. It's Snoopy pre-2.7 versus Snoopy post 2.7. So we realized that difference, and that's another 2 kilometers per second difference, kilometers per second per megaparsec. So at the end of the day, this is the F25 result. We were able to reproduce it to within very good accuracy. That's this row. And then when we update to the new Snoopy, and just refitting the supernova, it goes up to 72. If we just use the, and then let's just skip to the bottom row. And then when you add in all 35 or 55 calibrators that are in the literature, it goes up a little bit more.
Thank you.
So at the end of the day, we still think everything is consistent.
And she agrees.
I think she does, yeah.
Okay, good.
Thanks for that. I really appreciated the network strategy for this. It makes me wonder, what is the value of then looking for H naught to 0.1%? Are you going to keep pushing to?
Yeah, well, so I guess maybe my answer to that is that we've had some like early dark energy models, some early universe modifications to LAMP-CDM that have gotten H0 to 70. And so you could say, oh, well, our error bar was plus or minus 1.5 a couple of years ago. Maybe that's enough. And now I think it's harder to say 70. If you can get H0 up to 70 from the early universe, that might not be enough. So that's the context in which I would go for smaller error bars.
But the peculiar velocities is the level of 0.1%. You can't.
Oh yeah, so 0.1% is that's kind of crazy.
That's very
but pushing down a little bit more, I think, would be valuable. We may be there at that point. It depends on really.
Like the impact, like your point about the age of the universe seems like a great, huge impact and a great reason to be pushing to 1%, right? So from understanding the universe better.
Yes.
Is there a reason to push to 0.1%?
I would say, depending on what the theorists can tell us they can get H0 up to, we would want to make sure our error bar is below that.
Yeah, it's the importance of getting error bar small is that the statistical significance gets much higher. Yeah, so
right.
it would, but it's not so much that we understand the universe. We don't understand it, right? Based on this, there is a real issue here, and the question is what caused this change from the CMB data to this.
Yeah.
Something is wrong, something is not working. And actually theoretical attempts to explain it are not simple. They are very complex and they're not elegant. So, you know, usually you expect some elegant solution. In this case, there is none. So it's really a big problem theoretically to explain because it's not simple.
Mm.
Yeah, you can't do it with simple models. And that's why I never believed that it's
understandably.
Yeah, but now you're saying it's real, so then how do we explain it?
So do you believe it?
You know, it's a bad practice for a theorist to say the data is wrong just because I can't explain it. Morgan?
What does it take in this kind of network analysis where you have different tracers at different distances to look for like a curvature kind of term? Like
omega k?
For example,
okay.
Yeah, like is that something that you can measure across different tracers given this
across different tracers? I would probably say no. And in fact, the scope of this measurement is to be agnostic to models of cosmology. Really, this is both the supernova go out to redshift 3, but we don't look at those in this work. We stop at redshift 0.1. This is really H0.
Yeah.
And I'm not sure that. So maybe you're alluding to like we live in a void, and we do consider a scenario where we like chop out the bottom end of the Hubble diagram, and again, it doesn't do a whole lot for you. You have to.
So you always need one tracer across distance if you want to make a measurement of the evolving term. Yeah.
So Dillon, before we let you go, do you think this would be the next Nobel Prize in physics? Because it's a big issue for cosmology now.
Yeah, I guess the question is, will we be alive to see them award it? Because I don't know if they give it out just for 7 sigma discrepancy. We need to have something that's
some explanation.
Yeah, I would say that would be the tipping point.
Yeah. Actually, Avi, usually people come with a theory, and then it takes 50 years for the data to catch up, and then they give the Nobel Prize. Here, the data are already here now, it looks like. So until the theory comes, there's no Nobel Prize. I think you need to have a believable theory that explains why there is a discrepancy. And if that is a profound result, then there is a Nobel
so
Prize.
That's a challenge for someone in this room to
Yes.
find and then just buy a tuxedo and go to Scotland. Let's thank Dillon again.
It goes on.
Well, that's why I posted my slide. It's basically.
Does it work? Can you hear me well? Okay, perfect. Thank you for the invitation to present. My name is Maria Jose. You can call me Majo. I'm a PhD student at the University of Michigan working with Ted Bergen. And as the title suggests, I'll tell you a bit about the organic reservoir of the inner disk. I guess I should have said inner protoplanetary disk with JWST. So as a bit of context, we care about the chemistry of planet formation because it can tell us about the processes that lead to the formation of planets, particularly when we compare the current composition of observed exoplanets with disks. Obviously, this is a multi-stage process going from cloud collapse all the way to a form exoplanetary system like our own. But the part that I care about is this one where we have a protoplanetary disk. If we zoom in onto what this disk looks like, it's mostly gas. It's 99% gas, 1% dust. From this dust, we can create the cores of planets that they can eventually accrete an atmosphere, an envelope. And most of this gas is made out of volatile materials like water, CO2, or CO, which are the most abundant ones. And they have different sublimation temperatures from which they turn from ice to a gas species. So it is typical for us to define carbon to oxygen ratio based on how or where this different species sublimate. And we use this carbon to oxygen ratio to compare it to the carbon to oxygen ratio of exoplanets that has been measured. And now it's even easier to measure with JWST. So what does a disk actually look like when we observe it? So depending on where in the disk you are located, you will see different species or even different components of the disk. With ALMA, we use submillimeter observations, and we can probe both the solid and the gas component. When we look at the gas component, we look at the molecular species. In this case, for example, 12CO, one of the transitions is 12CO. But we can also look at the thermal emission from the dust continuum in this case. The only limitation, or one of the limitations that we have with ALMA is that it has limited spatial angular resolution. So when we perform observations, we're seeing mostly the outer part of the disk from like beyond 5 to 10 AU. But if we compare this with the population of planets that we have observed and that we can characterize or we have detected, most of them are inside of this. So when we try to compare with observations with ALMA, it's a bit difficult because we don't have that much of a sample size for exoplanets. And that's where JWST comes in handy, especially the mid-infrared observatory in JWST, or instrument in JWST. Since we're looking at mid-infrared wavelengths, we can see stuff that's closer to the disk, it's hotter. So we can actually probe that region where most of the exoplanets have been detected. And similarly, if we use the mid-infrared or the medium resolution spectrometer on MIRI, we can catch both the composition of the dust and the composition of the gas. So when we look at a spectrum, the continuum will be defined by the composition of the dust. In this case, for example, all of these bumps describe, these broad bumps describe that this source has silica and phosphoride. And if we look at the emission lines, we can see different species across the disk. So what have we found with JWST so far in terms of disks? So this is something that we knew all the way since Spitzer. So most disks have water, CO2, C2H2, HCN, and OH, which you can see here highlighted in this beautiful figure. And most of the lines that we see in T-Tauri stars that are like slightly higher mass systems are water lines. But one of the remarkable discoveries that we have made, which we kind of also knew from Spitzer before, is the difference when we look at lower mass stars. So this is less than 0.2 solar mass star, and this is higher than 0.2 solar mass, so this is average of how this look like. And you can see that most of those water lines disappear almost completely. And instead, the spectrum is dominated by hydrocarbons or just, in general, carbon carriers. But of course, there are outliers to this trend. So for example, we have seen systems that are very low mass, so 0.17 or 0.2 solar masses, and still have a lot of water lines, so a lot of water content. And vice versa, we have seen systems that are very high mass, so about solar mass, but instead have very strong hydrocarbon emission and multiple hydrocarbons detected. So we have this trend with mass, but some outliers to it. So there are two fundamental questions that can arise from this. So first, why are they different? What is the origin of these differences? Is it the stellar properties, the disk properties, or are we just looking at different stages in their evolution? And what is the extent of this chemical diversity? Are the species that we have seen so far really representative of the broader sample? So for the question regarding origin, it's at first difficult to answer if you don't have a large enough sample size. So what we instead did is look at the outliers. So one of those is the spectrum that I showed you earlier of a solar mass star that had very strong hydrocarbons. And the idea is that by looking at what could be special about the source in terms of physical parameters, we can tell why it's so rich in carbon, basically. So we did thermochemical modeling, testing different scenarios for why it was carbon enriched. And we reached the conclusion that it's likely because of sublimation of carbon grains. So rather than carbon coming from volatiles, it was coming really from solid grains that are evaporating and going into gas phase. So this is just showing the orange line here shows the amount of C2H2 that we detected in the source as a function of, well, in this case, not as a function of radius, but the models are the color lines as a function of radius, and they just show different C2O ratios. So you can see that we needed a very high C2O ratio for the source that's only attainable if you have extra carbon from solids. And another interesting thing that we found with this source is that it had a relatively low accretion rate from what it was expected. So it's around here for being so high mass. And we found that actually the sources that had relatively high accretion rates were very rich in water. So the color indicates that it's rich in water, whereas the ones that had relatively low accretion rates were rich in hydrocarbons mostly. But we could not extend this conclusion at the time to lower mass sources because there were not that many published at the time. So we proposed for a cycle 4 program that got accepted and will be observed next year, extending it to the edges of these very high and very low accretion rates. And another component of this project was also trying to prove this through modeling. So what we're trying to do currently is couple dynamical modeling with thermochemical modeling. So dynamical modeling essentially traces how these volatiles sublimate and how they transport across a disk. So here, this model is showing the amount, the color is showing the C2O ratio as a function of radius and as a function of time for different parameters, different stellar masses, and different viscosities, which are kind of transferable to accretion rate. So you can see that depending on when you observe the system or in which reservoir you probe, you will see different C2O ratios. The limitation of these models, though, is that they're only one-dimensional, and they don't go very far in terms of chemistry. They go up to C2H2. So what we're trying to do now is couple these with two-dimensional thermochemical models that can predict the speciation beyond the C2H2. And to answer the other part of the question, we also extended our survey. So this is a follow-up of a large ALMA program that was looking to measure the C2O ratio in the outer part of disks. But now we can also measure it in the inner part of disk with JWST. So we have a survey of 20 disks in lupus and 20 disks in torus. And they have, as you can see here, wide ranges of disk and stellar parameters. So disk radius, stellar mass, accretion rate, inclination, among many others. So what I'm trying to do in this project is exploring the detection rates across all these parameters and seeing how these correlate with the stellar and disk parameters. And here's show what some of the spectra look like. So you can see, for example, this one's similar to before, very dominated by water lines, some CO2, whereas this one is dominated by C2H2 and not that much water. And if I show you, for example, another one here, you can see instead it has very strong CO2, and this one has very strong HCN. So we see a lot of variability within this survey already. And one of the early results that we found, if we compare the two regions, the detection rates, is that organics were more commonly detected in lupus rather than torus. So you can see here that torus had no HC3N or benzene detections and only a couple C4H2 detections. And we think that this might be indicative of age evolution because lupus is slightly older than torus, but we're still looking into what could affect this. But overall, this program will allow us to test thermochemical models from which we'll derive C2O ratios, also dynamic and volatile transport models and physical models, and we hope to be able to characterize the full reservoir of the inner disk, understand the connection of inner and outer disk, since we have also C2O ratios from the outer disk with ALMA, and put the measurements of the C2O ratio and exoplanets into context. And that's my final slide.
Majo, is the chemistry affected much by dust or not significantly?
Yes, so in a way, there are many reactions that are only happen on dust or are mediated because of dust. But one of the other hypotheses as to why we see difference in the chemistry with JWST is because of the dust content affecting the optical depth, basically. So in the systems that have more dust, you're just seeing surface layers, where in the systems that have less dust, you can probe deeper into the disk and see more of the content. So that's also, there has been some results finding that the amount of C2H2 in water also correlates with the strength of the silicate feature at 10 micron. Maybe I can get to it. Maybe not. But the strength of the silicate feature at 10 micron. They're all continuously distracted. Oh no. There we go. So the strength of this feature, basically. And that's also relatively true, because you can check the amount of processing or the different types of processing. So in this case, silica and phosphorite are both crystalline minerals, where some observations have amorphous minerals, and crystallization is an indicator of thermal processing, so it was very hot in the disk. So that's also one of the things that people are looking into, basically, because there's a huge heritage from Spitzer looking at the dust composition that we can exploit now with JWST.
Eric?
So can you distinguish between water ice and CO ice and the gas phase?
Yes, so typically ice in disk is much broader, so it looks more kind of like the dust features, whereas the lines are very narrow, so you can easily disentangle them. Sometimes it gets trickier if you have like both of them at the same time, and that's more common in protostars, where you still have sort of a residual envelope, so you're catching more of that ice. But at this stage, you rarely see any ice, unless you're seeing the disk edge on, so you're really like going through the midplane and getting all of that ice.
I was wondering, when you put up a spectrum, say for a very low mass star, less than 0.2, and there's no water, and then well, is it all just frozen out on the dust grains, so that or are you taking that into account?
So at the distances that we are seeing, we think that it should all still be sublimated. So the sublimation temperature is like 160 K. So most of the lines that we would be probing here would be higher than that. So it could be that it's just frozen out further out into the disk.
It has to go somewhere.
Yeah. Is that, well, so one of the theories also that relates to carbon is the volatile, because you have these icy grains that are drifting into the star, the theory is that at first or early on you have a lot of water coming in, then it gets accreted into the star as the system evolves, and then you just have carbon coming in. So it could be that it's just gone to the star.
Okay, we're a bit late in our schedule, so let's thank
Hello, Theo O'Neill. I'm a third-year grad student here at CFA, and I'm really excited to share today some new results I've been working on connecting our galaxy's very local disk with its halo. So the disk halo interface in our own galaxy, how material is being transported from our solar neighborhood, potentially up to the halo and back again. And so traditionally, when we talk about disk halo interface in our own galaxy, we talk about a class of objects called intermediate velocity clouds, or IVCs. This is an important acronym for today's talk. I'm going to use it a lot. So IVCs, intermediate velocity clouds. I'm showing here on screen 2 maps of IVCs in the Milky Way. This is showing neutral hydrogen. And these objects are identified on the basis of their radial velocities being either too fast or too slow for what we would expect under galactic rotation. So these maps are showing in the top a set of inflowing IVCs, so clouds that are moving towards us too quickly to be explained by rotation. The bottom panel is showing outflowing IVCs, that's moving too fast away from us under rotation. We've known about these objects essentially since the dawn of radio astronomy. And because of these anomalous radial velocities, the preferred explanation for their origins is that they originate from a galactic fountain flow. So a model, like shown in this cartoon here, where supernova feedback or other forms of feedback drive enriched gas out of the disk, where it then cools through the halo and rains back down onto the galactic plane. So it's this returning or ejected flow that people tend to think may be responsible for this population of IVCs. And so we've known about these IVCs for over 50 years, and we've additionally known about 2 major asymmetries in the IVC sky that I want to draw your attention to. The first is that there are many more IVCs in the galactic northern hemisphere than in the galactic southern hemisphere. The second is that there are many more inflowing IVCs than outflowing. And so far, it's been difficult to pin down a comprehensive explanation for these 2 asymmetries. And the final thing that's important to know about for IVCs is that historically, constraining distances to these clouds has been difficult. The kind of gold standard metric for getting a distance to clouds in these maps or others is by taking pairs of stellar spectra where you have 2 stars at different distances. And you look for intermediate velocity absorption from this gas in these spectra. And so if you have one nearby star with no intermediate velocity absorption and a more distant star with some absorption, you can put together a bracket constraint of where this IVC is likely to be along our line of sight. And distances are really important for cloud physics. Without distances, we don't know basic physical properties like sizes or masses or pressures. So if we want to constrain our physical models of how galactic fountain flows affect our galaxy, how metal enrichment builds up through the disk over time, it's really important to know how far away these things are. And historically, we haven't had that many high-quality stellar spectra to actually pin down IVC distances. So what I'm going to talk about today is a new method independent of the stellar absorption spectra method of constraining distances and additionally 3D structures of IVCs in our nearby galaxy. What I'm showing here on screen is a parsec resolution map of dust extinction. This is centered around the sun, shown not to scale by the yellow dot. And this is extending out to 1.25 kiloparsecs from the sun in all directions, including critically in the vertical or Z direction, so above and below the sun, extending out of the disk of the galaxy. This map was made using a few 100 million Gaia XP spectra and was released last year. And so we typically think, based on past studies using these starlight absorption methods, that IVCs are limited to within maybe 1 or 2 kiloparsecs vertically above or below the plane. So this map, reaching up to 1.25 kiloparsecs vertically, allows us for the first time to start trying to map IVCs in 3D independent of these absorption measurements. So you can just go look for these structures directly in these 3D maps. And these maps are great, but unfortunately they contain no kinematic information. These dust maps just have our spatial positions of clouds. We don't actually know how they are moving. So what I've done in this work is try and connect kinematics from other tracers of gas to these 3D dust maps. So what we've done is connect this dust map, which is shown now in all sky projection on the left, to H1 21 centimeter emission, shown on the right is the H1 4-pi survey, which we use in this work. So by combining these 2 maps, by identifying clouds that match between dust and gas, we can get a simultaneous view of clouds' distances and 3D morphologies coming from dust, and their kinematics along the line of sight coming from gas. So we're creating a 4-dimensional map of clouds in the local interstellar medium. The way we do this is twofold. First, we identify clouds in a 3D dust map using a method that I'm really not going to talk about in any detail today. Feel free to come ask me later. But I'm working on developing a topological structure binding method, a way of identifying clouds in many dimensional spaces. We apply this method to pick out individual clouds in this 3D dust map. Once we've identified these clouds, we perform a morphological similarity analysis between the clouds in dust viewed on the plane of the sky and H1 at different velocities. So trying to find the best, essentially morphological match between a cloud in dust and gas. So one example of this process would be for one given cloud shown on the left is what its extinction looks like in 3D dust on the plane of the sky. On the right would be H1 at around negative 30 kilometers a second, which is the optimal morphological match to this structure. And by eye, these provide an excellent match in my opinion. So we're matching pairs of clouds between these traces to build up a catalog of clouds with 4D information. In total, we're able to build up a sample of almost 500 clouds mapped in 3D dust with H1 velocities. I'm showing here on the sky our map. The intensity of the clouds in this image shows their extinction. The color is showing their radial velocity along the line of sight. We have a huge variety of cloud morphologies and positions and properties in this catalog. Today, I'm really only going to focus on how different from what we'd expect under galactic rotation are these clouds' velocities. So trying to find the IVCs in this sample. To do this, we have to consider what we expect galactic rotation to affect our radial velocities. So I'm showing here on the far left a plot that basically all galactic astronomers will recognize. This is an LV diagram where L is galactic longitude, and then V here is the local standard of rest velocity. And you can see this characteristic sinusoidal pattern in the velocity here is imparted by galactic rotation. Additionally, for the first time, we can make what we're calling a ZV diagram. So this is vertical height above and below the sun versus velocity. And we can do this for the first time because of these 3D densities. We can then consider under some rotation curve for how we expect a gas to move in the Milky Way. We use Mark Reed's 2019 rotation curve to correct for the expected contribution of rotation to our observed radial velocities. And again, we're able to do this because we can directly measure cloud distances. So I'm now showing an L versus deviation velocity plot in this space, and the same for Z versus deviation. And what we see is that there are a few notable outliers of clouds in this space whose velocities are not compatible with rotation. So we define a threshold here of about 30 kilometers a second or so, where we find clouds that are not compatible with rotation. These are our intermediate velocity clouds that are really not moving as we'd expect. So in total, we find 4 IVCs. And for disk halo enthusiasts in the room, we find no high velocity clouds in this sample. So we find 4 IVCs in 3D for the first time. On sky, if we fade out, these clouds are pretty easily apparent. A few of these are well-known clouds. I'm showing up their names here. And then additionally, since IVCs have been studied for many years, but we haven't been able to correct for their rotations as a function of distance for a long time, there's a number of clouds that in the literature have been called IVCs that our work suggests are maybe more or less consistent with rotation. So I'll show this in a second. But 2 things I want to say here. First, all of our local IVCs that we find are located in the northern hemisphere. Think back to that very first slide, the all-sky IVCs map. The second thing is that the majority of our sample, by a small margin, but the majority, are inflowing with only one cloud being outflowing. So these all-sky asymmetries, the north-south and inflow-outflow in the IVC sky, are very much present in our own solar neighborhood. And then I'll additionally now show these set of literature IVCs that people have historically studied as IVCs. And so because there's been so much great work over the last decades in constraining distances to some of these clouds, it's somewhat useful to be able to consider how our cloud distances agree with these past literature constraints. So I'm showing here by the bars the existing best constraints on the distances to some of our clouds in the literature. These are typically from that starlight absorption measurement. And then I'll fade in here the actual radial 3D dust profiles of where these clouds are along the line of sight. And you can see that generally, for almost all of these clouds, these constraints in the literature agree extremely well. But we can go beyond this. For the first time, we actually have 3D morphologies of these IVCs, and beyond that, direct physical constraints on properties like masses and sizes. And so I think I'll leave it there, and then I'll put up my conclusions. So for the first time, we've been able to create 4D maps of structures in the local interstellar medium, so distances and velocities simultaneously. We've been able to use these to find a number of intermediate velocity clouds in 3D for the first time. And stay tuned for our paper where we talk about some other exciting clouds in this sample. So with that, I'd be happy to take any questions.
So here, if you had to guess, would you associate them with flows from the disk or with satellite galaxies moving around the disk?
Traditionally, people would expect these nearby IBCs to probably be galactic feedback. There's a few lines of evidence for these. Some of these have had their metallicities measured through absorption measurements, or additionally, many of them have dust extinction to a significant degree. So for a merger, which might have lower metallicity, that's a bit hard to explain. So my hunch would be their feedback, but I don't think we know for sure one way or another.
So I wonder if there's any correlation between like the medium density and the presence of the IBC. Because the reason is if you have an outflow, that's gonna collide with the medium. So if it has like a denser medium, so it will gonna lose its energy really fast, and the velocity is gonna slow down. So it might just fall into the IBC regime. So I was wondering.
That seems like one plausible pathway. The other kind of traditional thing that people have proposed to explain this inflow-outflow asymmetry is that perhaps the outflow phase coming from feedback is mostly hot and ionized, so it wouldn't even show up in these maps of neutral hydrogen that we're comparing to. But there's a variety of things you can think of in this space.
Well, we reached our time limit, so let's thank Theo again.